This is the second video on making predictions about an NMR spectrum for a structure. In the first video, we covered the top 3 structures that you see on this slide. In this video, we're going to cover the bottom 4 structures. Be sure you've had an opportunity to work through your predictions on your own before watching this video. For this molecule, we're going to see 2 types of protons. First, if we look at the protons in pink, these are methyl protons, so we expect their chemical shift to be about 1. And these methyl protons all see one proton, which is the blue proton, on the adjacent carbon. So the signal that represents all 9 of our pink protons is split by just the one blue proton, so that means that our signal is going to be a doublet. For the blue proton, this is a methine proton, and the signal for this proton is going to be split by all 9 of its neighboring protons. So we're going to expect to see a rather complex peak for its multiplicity. Technically, we're expecting 10 lines, but when we look at the spectrum, we'll see that we may not see all 10 of those lines. But overall, we're expecting something that looks like the signal for a proton that sees lots of neighbors. Which signal do you expect to have the higher chemical shift, the blue protons or the pink protons, and why? Here's the spectrum for the molecule. Can you match the predicted peaks to the actual peaks we see in the spectrum? In the actual spectrum for this molecule, we see the 2 signals that we would expect. For the pink protons, we are expecting a signal that integrates to 9 and has a multiplicity of a doublet. We see that in the peak that's at about 0.9 in our spectrum. We also see the blue protons show up with a chemical shift of about 2 in our spectrum. We were expecting to see 10 lines in that peak, and we don't quite see all of those lines, but we do see that the signal represents one proton that sees lots of neighbors. When I compare the areas under the peak for my 2 signals, remember that our signal for protons A has an integration for 9. That means that the area under the peak for that signal is 9 times greater than the area under the peak for signal B. So if for signal B we're expecting to see lots of lines in the spectrum, those outer lines are going to be getting smaller and smaller and smaller, and we may simply just not see those lines with the resolution that we have from our NMR spectrum. Without considering the multiplicity or the integrations on the peak, remember that you should have expected the methine proton B to have the higher chemical shift. That proton is bonded to a carbon that's bonded to 3 other carbons, and remember that the carbons are more electronegative than the hydrogens, and so that's going to help pull the chemical shift of that proton a little higher than the methyl protons, where the carbon that protons A, or the pink protons, are bonded to, is only bonded to 1 other carbon. For this molecule, we are expecting 3 signals in our NMR. The orange protons represent a tert-butyl group. We'll see an integration for 9, and because they're methyl groups, we expect their chemical shift to be at about 1. But they're not so far from that electronegative oxygen, so we also understand that it would be reasonable for that chemical shift to be a little bit higher than 1. For the multiplicity, we're going to have all 9 of those protons accounted for in one signal, and the adjacent carbon in each case has 0 protons. So we're going to see a very tall singlet that integrates for 9. For the green protons, these are alpha to an electronegative atom, so they'll have a chemical shift between about 3 and 4. The 2 green protons see 3 protons on the adjacent carbon, so that means that their multiplicity is going to be a quartet. For the blue protons, we have 3 protons that will be accounted for in the signal. We expect their chemical shift to be about 1, but because these protons are 3 bonds away from an electronegative atom, it might be reasonable for their chemical shift to be a little bit higher than 1. For the multiplicity of the blue protons, there are 3 of those protons, but they see 2 protons on the adjacent carbon, so that's going to give me a multiplicity of a triplet. Overall, I expect the green protons to have the highest chemical shift in my spectrum, and I expect my blue protons and my orange protons to have approximately the same chemical shift in the spectrum. Here's the spectrum for the molecule. Can you match the predicted peaks to the actual peaks we see in the spectrum? When we look at the actual spectrum, for the protons A, we expected this proton to be a singlet that integrates to 9 in the alkyl region. We see a singlet that integrates to 9 in the alkyl region, indicated by the letter A. For the green protons, we expected these protons to have the highest chemical shift in our spectrum because they're closest to the electronegative atom. We expected these protons to be represented by a signal that integrates to 2 and has the multiplicity of a quartet. We see a signal in our spectrum at about 3.5 that matches what we expect for the protons B. For proton C, we see a triplet right next to our singlet, right around 1. That triplet integrates to 3, and that tells us that we have 3 protons accounted for in that signal. And remember that the triplet tells us that those 3 protons see 2 neighbors. When you are looking at the peak and trying to determine the number of neighbors, you're going to subtract 1 from the number of lines in the signal to get back to the number of protons that would be on the adjacent carbon. Remember that when we have an integration like the tall singlet that integrates to 9, the ratio for the areas under the peak is 2 to 9 to 3. So by having a tall singlet that integrates for 9, that's going to make some of our other peaks with lower integrations appear smaller in our spectrum. The integrations, again, represent the relative areas under the peaks. If we look at the structure of pentane, we previously said that we had expected 3 signals in our NMR. And as we look at the signals in detail, for the purple signals, there are 6 protons that will be accounted for in that signal. It's a methyl group, so we expect the chemical shift to be about 1, and the multiplicity will reflect the fact that we have 2 orange protons on the adjacent carbon. That means that the multiplicity for the signal for the purple protons will be a triplet. For the orange protons, this represents a methylene group. And in the case of these orange protons, at the adjacent carbon in one direction, they have a carbon with 3 protons, and at the adjacent carbon in the other direction, we have a carbon with 2 protons. So these protons are different from one another, and they will split the signal for the orange protons differently. This is going to give rise to a complex splitting pattern, and we'll get into the details of that a little bit later on, but what you need to know is that the peak for those orange protons is going to look like a complex peak, and it will show us that these protons have many neighbors. So that will be reasonable for us to interpret from the NMR spectrum. For the green protons, their signal will have an integration of 2, a chemical shift in the alkyl region of about 1, and the multiplicity is going to be that of a pentet. That means that we will see the 4 orange protons contribute to the splitting of that green signal, and we're expecting 5 lines in our signal. As you look at these 3 sets of protons, which one do you expect to have the highest chemical shift? Which one do you expect to have the lowest chemical shift? Here's the spectrum for the molecule. Can you match the predicted peaks to the actual peaks we see in the spectrum? In the spectrum for pentane, we have a case where we will see overlapping signals. While technically there's a difference between the signal for B and C, a lot of times when we have long chain alkyl groups, a lot of our methylene groups will begin to blend together in an overlapping signal. So the peak that integrates to 1 with the slightly higher chemical shift represents all of our methylene protons in groups B and C in the spectrum. The methyl groups are differentiated. You see a very messy looking triplet in the NMR, but those methyl groups are differentiated from the structure. And you'll often see that to be the case. When you have a long chain alkyl group, several of your methylene groups that are very similar to one another with respect to their chemical environment will have overlapping signals, and we'll just see kind of a mess in the alkyl region. But the methyl group at the end of that chain often does show up as its own signal. We also see in the spectrum that we have a 1-to-1 ratio for our peaks. What we know is that there were 6 methyl protons, there are 6 methylene protons, and overall the areas under those peaks are equivalent. So that 1-to-1 ratio, we will need to make an adjustment to it, knowing that our protons are accounted for equally across both of those signals. In the structure of cyclohexane, we previously determined that there would be one signal in our spectrum, and we would expect the chemical shift to be around 1 in our alkyl region. Now, as we look at all of this information, this one signal is going to have an integration of 12, but that integration probably won't be given to you on the spectrum because all of our protons will be accounted for in one signal. So there would be nothing to compare the area under that peak to. And the multiplicity of the peak for cyclohexane is going to be a singlet. So in this case, even though we have protons on the adjacent carbons, because all of the protons in the structure are equivalent, they will not split one another. So a very important thing to remember with NMR and your multiplicities is that equivalent protons do not split one another. Equivalent protons do not split one another. So in the spectrum for cyclohexane, we see our one peak, we see it has a chemical shift of about 1.5, and all of our protons are accounted for in this signal. It's a very clean singlet, reinforcing the fact that all of our protons are equivalent.